Okay, in these next two examples, we're going to be taking a look at application, where we are going to be using equations that involve radicals or square roots. So our first one says the time in seconds for the pendulum of a large clock to make one swing is given by this equation. It tells us L is the length of the pendulum in feet. So if one swing takes 4 seconds, how long is the pendulum? This right here is the pendulum. So imagine this clock super huge. All right, this equation that we're given here is going to tell us the time that it takes to make one swing. Okay, so if one swing takes 4 seconds, how long is the pendulum? So we're told the time in seconds here, 4 seconds, and we're wondering how long the pendulum would be if it takes 4 seconds for one swing. So we know that time is 4 seconds. So we're going to replace the t in our equation with a 4. And let's go ahead and rewrite it. We have 4 seconds equals 2 times the square root. Now this right here is an L, so I'm going to make it in cursive so you guys can tell there's my L, length of the pendulum divided by 3.3. Okay, so here is my equation. Now what we will be doing here is solving it in order to figure out the length of the pendulum when it takes 4 seconds to make one swing. All right, so let's get started. Our goal here is to find the L. Do you see how the L divided by 3.3 is trapped under the radical? Let's leave it there. We're going to undo the outside first. Okay, so we're going to divide by 2. So we would get 2 equals, and then radical length divided by 3.3. All right, then in our next step, we're going to take out the L divided by 3.3. Let's take that out of the radical. So right now it's trapped inside here. We're going to square this side to cancel the radical, and we're going to square the other side as well. This gives us 4 equals L divided by 3.3. All right, now my last step here is to get this L by itself. I see it's being divided by 3.3, so the opposite would be to multiply by 3.3 to both sides. So that will cancel, and we get length of the pendulum is equal to 4 times 3.3. And with a calculator, that's 13.2. So the pendulum is about 13.2 or 13 and 2/10 feet long. So imagine this clock. If the pendulum's over 13 feet long, the pendulum that swings, this clock has got to be huge. Pretty cool. All right, so we solved that equation. Let's go ahead and take a peek at the next one. Here we have another application with a different radical equation. Special airbags are used to protect scientific equipment when a rover lands on the surface of Mars. The function that's given here approximates an object's speed as the object hits the ground after bouncing x feet in height. So we're wondering, how high would the rover bounce if it was traveling 40.2 feet per second? So imagine this rover here is traveling a little over 40 feet every second, and it's going to land on the surface of Mars. When it lands, it's going to bounce. We want to figure out how many feet is it going to bounce when it's traveling 40.2 feet per second. Okay, so let's use the equation that we're given here. I think we're going to have to plug in a variable. Oops, sorry, trying to get this to work. Okay, so the rover's traveling 40.2 feet per second. That's the speed. So that's going to be the s right up here in the equation. Remember this x that we're solving for? That x is the bounce. That's how many feet it's going to bounce after it hits Mars. Okay, so I'm going to replace the s with 40.2 feet. So we're going to go 40.2 equals, and then we have 3/5 radical 64 times x. Remember, x is the bounce. All right, so let's get ready to solve this. What do you think will be our first step? Do you see how the 64x is trapped under the radical? Let's leave it there and let's undo this. Do you see how this is times 3/5? Well, what we can do is we can divide by 3/5, or we can even multiply by the reciprocal. But do you notice that the number on the other side is a decimal? It might be easier to work with 3/5 if we change it to a decimal. So if we take 3 divided by 5 in our calculator, that is really just the same thing as 0.6. So this is really 0.6 times the radical. So instead of dividing by 3/5, let's divide by 0.6. So I'm just changing that to a decimal. And then I'm going to do the same thing over here, divide it by 0.6 or 0.6. It might be easier just to do in the calculator. So I've got radical 64x left on this side equals, and then in the calculator 40.2, and we're going to divide it by 0.6, which is 3/5. And that's going to give us exactly 67, and it worked out really nicely just keeping that as a decimal. Okay, so now let's get the 64x out of the cage, out of the radical, by squaring this side. That will cancel it, and squaring the other side as well. So 67 to the second power is 4,489. Calculator is super useful for that. Over here, the 64x comes out of the radical. Oop, there we go. And of course, to get the x by itself, we just divide by 64 to both sides, and x equals, in the calculator, 4,489 divided by 64 gives us, well, we're going to have to approximate here. It's little squiggly lines here. Approximately 70.1 is what I'm getting. So let's answer the question. The rover would bounce about 70.1 or 70 and 1/10 feet. So at that speed, when the rover's traveling at that speed and lands on Mars, it's going to bounce on impact. It's going to bounce about 70 feet. But remember, those special airbags that are inside are used to protect the scientific equipment when they land because of that bounce. Pretty cool. All right, thanks for joining me for the application.